Okay, let's see how this works out. My machine's acting kind of funky right now. My machine's acting kind of funky right now, so let's hopefully there should be no problems. But this thing's not liking me this morning. There's no doubt. So let's go back and look at what we did last time. Okay, so what we'll do here is that let me get into my OneNote. I don't know what's going on. So if I look at what we started to do, we started to develop phasor relationships in this language here. And well, I mean, in some shape or form, I got to get this to work. Let's try this. The problem is I'm not seeing my OneNote. I don't know what is going on. I think you should see it now, right? Hopefully. So what I want to sort of like really just talk briefly about is that we're moving from, I guess, time-dependent solutions to phasor-dependent solutions. And the way we do this here is that we essentially doing a mapping. So if I was to sort of like give an overview, if I was talking about a phasor concept, the phasor concept is something like this here. Is that in AC circuits, the circuit always oscillates at the driving frequency. And this is what we defined as omega. But this driving frequency is really always a constant, and never changes. The only thing that changes is amplitude and phase. And so what we can do here, so if I write our solution, so our solution is then written into complex form. And the whole point of that form is that we would write a solution that, you know what, let me write this just a slightly different way. Our solution always had this form. And now that what we're seeing here is that I can write a solution in terms of an amplitude and a phase, but and these were complicated functions. And the reason why this was complicated is that this guy is frequency dependent. And because they're frequency dependent, they lead to really ugly, amplitudes when we go to solve that differential equation. And that's not what we want to do, right? That's a horrible thing to want to do. So what we want to do here is that we want to essentially come in and sort of like try to set it up so that we only, how do I say this? So that we make it as easy as possible. So what we do here is that when we transform into the complex plane, this function is now a complex function. And the way we're going to write this is we're going to write this in polar form. And in polar form, we're going to have some amplitude, which I'll call the maximum amplitude of whatever that quantity is. And then I'm going to get j to the omega t plus theta. And so when you look at this, what we find here is that I can separate this apart. I could separate this with the amplitude and the phase part times e to the j omega t. But one of the things that we said here is that, check this out. This is our changing amplitude and phase. I mean, we already saw that the amplitude and the angle theta were changing, were frequency dependent. So we can isolate this thing without combining it with the cosine. And then this other piece right here, this piece is not changing. It's always going to be like that. So what we find here, with phasors at least, is that if we focus only on the changing amplitude and phase, this portion of the solution is called a phasor. And all it is that a phasor, by definition, is a complex vector, written in polar form. And our job here is to really do that. And so when we write this complex vector, we'll typically write it with an amplitude, e to the I theta, and it's very common to also write it like this. So this is our definition of a phasor. It's a complex vector in polar form. And so what you're seeing here is that we could move very easily between solutions. So if I have a time domain solution, we typically write this as, let's say, x of m cosine of omega t plus theta. And then if I have my frequency domain solution, we're going to write this as x of m of e to the j omega t plus theta. And the way we move back and forth with this is through Euler's relationship. So what I do then is I do the following thing. So if I use Euler's relationship, so what we do here is that we sort of do the following thing. We start in the time domain, and then what we do here is that then we do a transformation or a mapping, if you want to do that, a transformation into the complex plane. And this is what we mean by a phasor circuit. A circuit in the complex plane. So then what we do from here is that now we solve the circuit problem. Okay. So now that we've solved the circuit problem, so now that we solved the circuit problem, we then transform back into the time domain using Euler's relation. So in other words, we have an assumed solution which looks like this. We then write this as x of m e to the j in this form. Okay, I'm sorry, I'm not doing. Then we transform it into like this. And then when I use Euler's relationship, then what I do here is then I take the real part of the complex vector, which then means that I'm taking the real part of e to the j omega t plus theta, which then gives us x of m cosine of omega t plus theta. So we can easily get back that solution without a problem. So that's roughly what the idea is. So the thing about this is that we got to be really careful about this. We have to make a choice between what do we mean as the standard AC function. So in AC circuits, the standard reference can either be cosine or sine functions. Most people use the cosine as the reference. It's the standard. In fact, it's, you'll see that when people are actually solving some of these things, when they find that that it's written in sine, it actually pisses people off. I mean, it's not that big of a deal, but nonetheless. And so what you find here is this, that if a source is a sine function, one must use trig identities to rewrite sine into cosine. And of course, what that really means here is that there's a phase. So for example, let me give you a sense of this. As an example, suppose that you have some current that's written as 4 cosine omega t minus 80 degrees. Now note I didn't write that into pi. So now, if I now make it into a phasor form, right? So now in phasor form, since the omega t term always cancels out, this is really a phasor current written as 4 to 8 to the negative 8 degrees amps, of course. Okay? Now, suppose the voltage is written as V of t, which is then written as A sine omega t minus 20 degrees. Well, that's no good. So this immediately tells us here not in terms of cosine. So the very first thing that you got to do here is that you're going to have to transform this thing into cosine because that's the reference. So then this tells us here is that we must transform sine into cosine. It's not that it's a big deal, but that's what we have to do. And so what we'll do then is that we then say, we know that the phase between sine and cosine is 90 degrees. So I can write it like this here. So I could then come in here and say, okay, so I have sine omega t minus 20 degrees. And then I know that the difference between sine of A is then going to be cosine of A minus 90. I could have chosen plus. It doesn't really matter here. But if I do this, then I can then transform, and then I got to add that phase of 90 degrees. So therefore, now I have a cosine function, which will be 20 minus 90, which then really means cosine of omega t minus 110 degrees. So in other words, V of t is really 8 cosine of omega t minus 110 degrees. So now, in phasor form, I can now write this as V equals to 8 110 degrees with the minus sign. Now, the reason why that's important here is that now the importance here is that now one can easily compare phases between I and V because now they're in the same form. So that being said here, what I want to do then is that I want to just go in briefly and see what we did last time. We were talking about phasor relationships for RL and C. We assumed that we had an AC resistor, and because the resistance is linear, doesn't have a derivative term, I could then come in here and we found out that we have this reactance R, X of R, which was just R because there's no derivative term in this thing. And we found here is that as a consequence, if I compare the current and the voltage, just like we were just talking about, there is no phase difference between these two. So when I look at this vector, the reactance does not depend on frequency. Actually, that's not exactly true. At ultra high frequencies, resistors do have a frequency dependence. And so our vector in the complex plane has no imaginary part. It all lies in the real axis. Then we went on to AC inductors. And when we solved this, we found out that there's sort of like this AC resistance. And in other words, it's called inductive reactance. And we got to be really careful because reactance implies that there's no heating, but it impedes the flow of current. So when we go in and we calculate we looked at the reactance amplitude, we saw that it depended on, it was equal to omega L. And so it's a linear function. And this is no surprise here, because as I increase the frequency through a coil, the back EMF gets so huge that it would open the circuit and kill all the current in the circuit. So we know that that must be the case. And then if we look at the phase, looking at our relationships, we have to write J in polar form, always. And in polar form, you get this positive pi over 2 or 90 degrees. So I got a positive phase. That means here that when I look at the current is shifted to the right by pi over 2. And so what we're seeing here is that the voltage leads the current, and we said here that it leads by 90 degrees. Okay, and the acronym that people typically use is ELI, and E is the voltage. So you could really see this in two ways here. We could say that this is the inductor voltage, and at the same time leads inductor current. So that's what that really means. And what we're seeing here is that in the complex plane, you literally have a vector along the J-axis. So that means every time I see an inductor in a phasor circuit, I don't write L, I write J omega L, because it's now in the complex plane. And then we didn't finish the capacitor one, but we started moving along the same way here. And what we ended up finding here is that when I looked at my reactance, it had an amplitude, it had a phase, or I could read it like this in the complex plane here. So what I think I'm going to do here is that I'm going to copy this and move it to the other page so that I could finish it there. So I'm going to copy here. Then I'm going to go right here. And then I'm going to paste this guy right here. So now we were talking about Ohm's law for the capacitor. And we end up getting this relationship, this ratio right here. So VC over IC is this whole relationship right here. And our job is to analyze this thing. So if we want to analyze this thing, what we want to do here is that we want to look at the amplitude, and then we want to look at the phase here. So one of the things that we really want to think about here is that what does it physically mean when I have a capacitive reactance? Well, it has units of ohms, so it acts like a resistor. It's not a resistor, it's a reactance. Resistors don't have frequency dependence. Reactances do. And what we see here is that if I look at this thing, as I plot this at low frequencies, or exactly zero, this thing climbs up to infinity. So it acts like an open circuit at high frequencies. And that's not a surprise here. And the reason why that's not a surprise here, because if I have a low frequency and that time is greater than 5 tau, what I'm going to do here is I'm going to get a fully charged cap. And if I get a fully charged cap, of course the current in that branch is going to go to zero. Not a surprise. However, if I have really high frequencies at high frequencies, what you're going to find here is that as soon as charge lands on the cap, the charge is immediately pulled off. So what this implies here, if I do that, then VC will be equal to 0. And if VC is equal to 0, any voltage that's 0 implies that it's a short. So at high frequencies, you could see here that the reactance of the capacitor goes to 0. It starts to act more and more like a short. And so this reactance makes physical sense because of that reason here. So then the last thing that we want to really look at here is that we want to go back and we want to look at the so-called phase here. So let me make sure that I'm set up here because I really wanted to set this thing up right. Yeah, I was fighting with my computer this morning that I didn't get a chance to fully set up here. So my apologies about that. So what I want to do here is that now I want to look at the phase. Okay, so what do I know about the phase? Well, what I know about the phase is this here. We're looking at what? We're looking at when the current goes through the capacitor, it changes the phase of the current. And what we typically do, remember, just to remind you from last time, the voltage source here has no phase. And because of this, it tells us that Vs is then just going to be V max e to the j omega t. So it has to be that way. But the capacitor current develops a phase. And what we said here is that the way we looked at this guy here is that how did we write this down? The way we wrote this down here is that we had VC, IC, and then we had minus JXC, which is the same as XC e to the minus J pi over 2. So what you're seeing here is that if I rewrite this thing, what this is really telling me here is that VC is then going to be XC times IC e to the minus J pi 2. So what this tells us here is that the current shifts not to the right, but to the left. So the current shifts to the left this time, not the right. And as a consequence of this, what we see here is that the current leads the voltage, not the other way around. So I'm going to do a little bit better job of this here. So what I'm going to do here is that if I plot this thing, I'm not going to try to do multiple cycles here. That shit screws me up when I try to do that. So what I'm seeing here is that you could imagine that here's my voltage here. Okay, so how do I draw my voltage? Let's say that it looks like, let me draw the current first, actually. So the current's going to look something like this. Okay, there's the current. And so if I look at the voltage then gets shifted. So this here is the voltage of the cap, and this guy here is the current of the cap. And what you're seeing here is that you could see right here that because of the shift to the left, in this case, it would be shifted by how much? It would be shifted by minus, well, it'd be shifted by pi over 2. So that means that the difference in phase between these two, of course, is 90 degrees. But there's that minus sign there. Okay, there's this minus sign. And so what typically happens here is that, of course, they use an acronym. And the acronym that we find here is that because of this, we say this. We say here that the current leads the voltage in this case. And so what do they say? They call it ICE. And again, E is the voltage. And so that it looks like that here. Okay, so now that I got that, what does it look like in the phasor language here? Right, because if I look in the phasor language, remember, we're trying to plot vectors in the complex plane. So then if I look in the complex plane, the capacitor vector looks like how? The way it looks like is that I have a vector that looks like this. That means here's my J. So that means I now have a vector that points directly down. And this will then be minus JXC. So if we now add the other two, right? So then adding the other two, you could see here that now I have situations where I'm going to have my JXL, my minus JXC, and my XR. So I have these vectors, and then how we interpret these vectors is the whole goal of phasors. And one of the things that we should do here is that we should sort of like come back and just kind of think overall to see what actually happens here. And so our goal here is that it's going to look something like this here. So now we have a circuit. And these circuits, what we're going to do now is that we want to solve them in a complex plane. And our goal here is to essentially try to understand physically what they mean. So how do I write this? So I think what we should do here is that we should try to summarize this thing. Okay, we need to sort of summarize. So what we typically do here is that we start in the time domain with RLC. And remember that in the time domain, if I have 6 capacitors and inductors, that's a 6-order differential equation. I don't know how to do that. So how do we solve these things in a nice, simple way? And so what we do then, we start on the thing, um, and then transform into the complex plane. What exactly does that mean? What that means here, I start with R, and I do what? I replace it with XR, which of course is still R, and it has a phase of 0 degrees. Then I start with L, and then I transform this into my circuit that looks like this, where this phase is 90 degrees. And then I transform this into here, and this phase is minus 90 degrees. So now what we're doing here, we're essentially going to be doing vector algebra in the complex plane. And I literally mean vector algebra. That means if I have a capacitor, a resistor, and an inductor in series, I treat them as linear elements. They have units of resistance. That's linear. And so what you're going to find here is that we do the algebra. And once we do that, if we choose to, we then transform back into the time domain to actually do that. But what I want to do here is that I'm going to try not to transform back because it's more important to interpret what is happening in the phasor circuit here. And so now what we're going to do here is that now we want to interpret what it means to be a phasor circuit. And the way we do this here is that we now, so if I was to give you an analogy, what we did before here is that when we had series and parallel, we computed the equivalent resistance. And then for the equivalent resistance, we could use it to do what? We could talk about it in the language of how do I say it? In the language of, series, where we could then use the series resistance to use the voltage divider rule, or we could talk about the equivalent resistance of parallel circuits, and then we could use it, let's say, using the current divider rule. What we find here is that we have the equivalent resistance. So the AC equivalent resistance is defined as the impedance. So they don't say AC resistance, they say impedance. And the impedance is almost universally defined by the vector Z. And if I was to look at this thing in the complex plane, in rectangular coordinates, it looks like this. And of course, in the complex plane, I can write this like that. And so the way we calculate the magnitude and the direction of this thing looks like this. So if I look at the magnitude, then z here is going to be r squared plus x squared square root, and the angle is going to be the tangent inverse of the reactance divided by r, where x is really has to be, it's got to be, well, the jx is going to be xl minus xc. So let's look at this thing. What are the possibilities of a reactance like this? Well, one of the things here is that let's look at the phasor diagrams. You could imagine a scenario that it looks like this here. I have a vector that's two squares here. So this is XL. And you could imagine that I have a vector that looks like this, XC. And let's say that I have a resistance that looks like this. And you could see here that in this situation, XL is greater than XC. So what this tells me here is that if I do my vector addition here, you could see that the XL is two squares, whereas the green is one square. So what I'm really seeing here is that I'm going to get a reactance. How do I say this? A reactance that looks like this here. That's going to be X. And then if I look at my red here, my purple, it's going to look like this here. So what this tells me here in the complex plane, I could then go calculate the impedance. So if you look at this, you could see here, if I go in here and I complete the parallelogram rule, you could see here that I'm going to get an impedance that looks like this. So in this case, your finding here is that the impedance of the circuit acts more inductive than capacitive. So immediately we could say if it's more if it's more inductive, then that immediately tells us that the voltage leads the current. And at high frequencies, the current decreases. And remember, why does it decrease? Because remember, what does this thing look like? If I plot XL, and this is omega, we already saw that the frequency, that the reactance increases with frequency. We can immediately say that. So if I look at the other situation, let's say that it's the opposite way. I have a longer reactance and for the capacitor and a smaller reactance of the inductor, where I'll say here that the resistor looks like that. So in the complex plane, what we're saying here is that now I know what the impedance is going to look like, because we can see here that in this case here, what do we have? What we have now is that the reactance XL is now pointing below. And if you look at this guy here, you can see that this guy tells us that it's going to be below the axis. In other words, the impedance in this case is now here. So this tells us, because it's pointed along the direction of the reactance of the capacitor here, that tells us here that the impedance of the circuit acts more, I noticed I missed here, capacitive than inductive. And again, that tells us, a couple of things right away. We'll see here that the current leads the voltage here. And if it leads the voltage, then that also implies here that at low frequencies, the current will decrease. So how the impedance behaves is going to tell us what's going on here. Okay, how the impedance behaves will tell us what the circuit is going to be doing here. And so we play this game here. Now this is obviously fairly simple here. We're only talking about, two vectors at this point right here, or three vectors. Very, very simple vectors. But that doesn't have to be the case, because now, check it out, right? By the way, I should have done this because I did it in the other one. If I look at this case here, if this is XC and this is omega, we saw here that it actually looks like this. That's why the current decreases. So now I got 1, 2, so then check this out. Here we go. Capacitors, and inductors behave linearly in the complex plane. Therefore, we treat them as good old resistors. So no more differential equations, right? That implies no more differential equations as before. That means if I see series impedance, right? So in other words, if I have a resistor, a capacitor, and an inductor in series, I treat them as regular resistors. So then that means here that if I go look at the total impedance for this thing here, it's going to be Z1, Z2, Z3. So if this is R, this is C, and this is L, then that means I'm literally going to come in here and I'm going to write this as R minus JXC plus JXL. I treat them in series. And I can do the exact same thing for in parallel. So if I have R, C, and L, then I know that Z parallel is then going to be literally Z1, Z2, Z3, which then just means R minus JXC plus JXL, and that's where we're at. So that means here that if they're linear, now that I have series and parallel, now I could think of terms of Ohm's law. Ohm's law just says then that the voltage across any element, right? The voltage of any element will then be its impedance times its current. So this implies here that if I want the voltage across the resistor, that's just XR times I. Or if I want the voltage across the cap, it's going to be XC times I. Or VL is going to be XL times I. So we're using all of those same ideas of Ohm's law. And so then we could just quickly summarize everything. So if I go to 4, I then could come in and just say what? Now, we can use all those DC techniques from the past. That means I can use, well, I could always use KVL, but really, it's really about VDR, CDR, node, mesh, Thevenin, right? Thevenin, Norton, or anything else there to them. The problem, right? However, right? There's always a however. There is a cost. The Phasor algebra is painful. It's just painful. Number crunching and Phasor algebra, oh man. And as an example, let's just kind of look at a simple example. And it goes something like this here. So let's look at Phasor algebra. What this kind of looks like, I don't think it is. I don't think it's the same thing here, but this could look like maybe something that you got as an equivalent resistance from something. And what I wanted to do here is that I just kind of want to just show you what do I mean here. What do I mean by painful here? So what you're seeing here is that I'm just multiplying, really, and dividing by two things here. And so what you find here is that this is what you typically got to do here. So in regular algebra, by the way, this may be just one term in a long calculation. And what you're finding here is that you must master complex algebra. And what I mean by complex algebra, that means algebra on the complex plane. And so there's a couple of things that we can do here. So let's calculate this thing so you can see what I mean by this. So the first thing that we want to do here, so what we want to do here is that we want to always put things into polar form. Why? Because polar form implies what? It's a phasor. We want it in terms of phasors. Why do we want it in phasors? Is because it's just easier. That's why. It's just easier. And so the first thing that we'll do here is that let's just focus on the numerator. So if I take the numerator we could see that the numerator is really 5 36.9 degrees times 10 minus 53.1 degrees. And so immediately what we do here is that we convert this into phasor form. So in other words, you could see here that I'm going to multiply these two together, and then I'm going to convert 36.9 into a complex exponential. So what I'm really seeing here is that I'm really seeing this here. Maybe I should do this in 2 steps. So the first one here, yeah, I think I'm going to do this in 2 steps just so that I'm real clear. Let's focus on the first one right here. So if I focus on the first one, here's what I see. Well, I'm going to convert that into polar form, so that's e to the j 36.9 degrees. That's the first one. And if I do the second one, which is this guy here, I'm going to convert that into phasor. So this will be 10 e to the minus j 53.1 degrees. And so what you're seeing when you do this, then I could now multiply 5 times 10, and I could then add the exponents because that's part of its algebra. So then I'm going to get 50, and this should be e to the j, and it should be 36.9 minus 53.1 degrees. So then at the end, of course, I'm going to get 50, and then I should have a negative number, which will be minus j 16.2 degrees. Right? Not too bad. But let's look at the denominator. So if I look at the denominator, whoa, look at the way I spelled it. Let me try that again. I know there's an I someplace. So if I look at the denominator, note that that's in rectangular form. So immediately I got to put that into polar form. So then this would be 4 plus j3 plus 6 minus j8. So if I put that all together, this is going to be 10 minus j to the 5. But wait a minute, it's got to go into polar form, right? It's got to go into polar. So if I go into polar form, that really means that this should be 10 squared, 5 squared, square root, which is then 11. And then the angle here is theta, which will be tan inverse of minus 5 over 10. And in this case, it should be minus 27 degrees. So this tells me here is that now I have a polar vector, which is 11 e to the minus j 27 degrees. So now, if I put this all together, I then have the following algebra here. So I multiplied the first two terms, right? So now if I go look at this, I have my, if I look at my total expression, I have my numerator, which is then 50 e to the minus j 16.2 degrees, divided by my denominator, minus j 27 degrees. And so if I compute that, that should be about 4.5. And then I'm going to get e to the j 10.4 degrees. So let's say that for the sake of argument, this was the equivalent impedance of a circuit. What does this mean here? If this was the equivalent impedance of a circuit, it then says this here. It says the following thing. It says that I have a vector, and that vector z is like this. It has a length of 4.54, and it has an angle of 10.4 degrees. And this is where I'm plotting this guy in this axis here. So therefore, when I look at this impedance, this is more inductive. And if it's more inductive, then that means here that at higher frequencies, I expect that the impedance to increase. And then I also expect that the voltage is going to be leading the current. So there's a lot of these things that we have to sort of like deal with. So the last thing that I really want to look at here is that I want to do the following thing. Let me go get this applet that I apparently deleted. And so the last thing is that what the hell does this thing mean? And what we're going to do here is that we're going to go in and we're going to look at this thing here. So if I was to, if I had been a little bit more clever, I probably would have converted. Well, let's convert this into rectangular rectangular coordinates, just so you could see what I mean by this thing here. So let me get my calculator out, and you guys should also get your calculator out because you should never, ever trust me. So what we want to do here is that now let's transform this into rectangular coordinates. So what I do then is that I come in here, and the way I do this here is that I apply Euler's relationship. So then what I'm going to do here is that I can write this as 4.54 e to the j 10.4 degrees. And I got to be careful here. 10.4 degrees. Let's just leave it like this. So it's going to be 4.54 cosine of 10.4 plus j 4.54 times sine of 10.4. So if I compute these numbers, what am I getting here? So I'm going to get a number that reads 4.47 plus j, and then I'm going to get and then this is going to be 0.82. And I'm going to say that this is in ohms. So what I'm seeing here is that I'm really seeing the following thing here. What I'm seeing here, so if I plot this on a phasor diagram, it looks like this. So here's my phasor diagram. And what we're seeing here, of course, this is J. So now this guy right here is my real part. And you could see that this guy right here is my imaginary part. So what you're seeing here is that you're really seeing something like this here. You're seeing that there's this little tiny guy, and this is the reactance. And then you look at the resistor, and the resistor is like much bigger, right? It's almost 5 times bigger. So it's going to be 1, 2, 3, 4, 5. Let's say it comes all the way out to here. So you could see that this is much bigger than that. And that's going to be my R. And so what you're seeing here is that you could see that from the parallelogram rule, I am going to have an impedance. Right? I'm going to have an impedance. Now, one of the things that we mentioned here is that when we solve phasor circuits, e to the j omega t cancels out. But it does not disappear. It does not disappear. So what is this z vector doing? It's rotating. What do I mean it's rotating? Because remember, with everything that we have, so when I look at z, yeah, it's z, and then we have e to the j theta, but what canceled out is that j omega t. So what really is happening is that this piece right here, this causes a constant rotation in the complex plane. It's an AC circuit, so it has to be doing it. So that means that this vector here is actually rotating at omega. And what you find when you look at this thing here is that if I come over here, we always find that the magnitude and the angle never change. Those angles are always the same. So when I look at this angle here and I look at that z, that's what it looks like. So let me go show you what I mean by this. So if I go do a new share here, I have this very, very good applet from Fent. And it's a simple AC circuit. And one of the things here, look at the phase diagram right here. You can see the blue here is the voltage. Here's the current. So what I'm treating this guy here is not voltage and current, but that's what we ultimately are going to be calculating. Is that what I'm showing you here is that imagine that there's a vector summation between the blue and the red. So you could see that this vector is going to be pointed somewhere between these two. So now check this out. So the way I have my picture, it looks like this here. Look at the rotation of these guys. So what I'm going to do is I'm going to stop it when this gets to the axis here. This is effectively the picture that I'm showing you right now. And so what you're seeing here is that now if I stop doing this, this is my impedance vector. This is my impedance vector in rectangular coordinates. So if you look at the blue, in this case, that's going to be my x component. And if you look at the red, that's going to be my r component. So now, what does a phasor really look like in the complex plane? It's this. It's rotating. And look that the length of the blue and the red never change. So therefore, the sum of those two vectors never changes. The impedance is constant. And all it does here is that it's rotating. And then every once in a while, what we're going to do here is that we're going to stop it. We're going to say, okay, now we're going to do a calculation right there. That's what a phasor vector really looks like. So when we go start calculating phasor vectors, this is what I want you to think about. Okay? I want you to think about what this actually means, because that's exactly what we're going to be doing now. So now that we have this, hopefully this image of what a phasor is, we're going to calculate, and then I will try to give you some intuition as we go along as to what is going on. Okay, so the time has come. Let's just start calculating now. So all I'm going to be doing is that I'm just going to be doing calculation after calculation after calculation, just to get you to see what it means here. So here's my first calculation. So we should start back at very simple stuff, right? Very simple stuff. And the most simple thing to do is to calculate impedances of a circuit. Here we go. So we should start off here by calculating everything. Okay. We'll start off as simple as possible and then just crank right through this. So here we go. So my job is to just beat you over with examples so that you know exactly what to do. So right now, what we see here, we start with a time domain circuit. And we said here that that's not good enough for us because remember, if we want to go solve this thing, this is a second order differential equation, right? So we start with the time domain circuit that requires a second order circuit calculation. And it's a messy one too, right? Because you got the sines and the cosines. So what we do here is that now we convert this into a Phasor vector problem. Okay, so here we go. So what do I know? I know that the frequency they tell us is 10 kilohertz. So the first thing I got to do is I got to go change that. So if I go change that, what I really do know now is that I really got to change this to omega, and omega is 2 pi times the frequency. So then that means here that I'm going to get 2 pi times 10 to the 4. So I'm going to leave this as 10 to the 4 rads per second. So I now know what omega is right now. So now that I have omega, I now convert into a Phasor circuit. So to convert this into a Phasor circuit, I know that XR is of course R. So in this case, it's just 36 ohm. No big deal. But then if I look at XL, we know that XL is of course J omega L. So then I got to start putting in the values. So if I look at this, this is going to be J, and then I get what? 2 pi times 10 to the 4. Excuse me. And if you look at L, you could see that L is what? 10 to the negative 6. So if you look at this thing here, oh, no, I'm looking at the inductor. That's 160 times 10 to the negative 6. So what you're seeing here is that if you multiply this whole thing out, and you're going to see the sig figs become an atrocious thing here. And our answers they become quite painful, as you'll find out. That's a lot of sig figs for this problem, right? So if you really do this thing out, I'm going to approximate this to J10 ohms. So now I have my reactance of the inductor. Now I'm going to do the same thing for the cap. So for the cap, I have XC. In this case, it's going to be omega times C in the denominator. And if I just do the exact same thing, this is going to be 2 pi times 10 to the 4. And then this guy's going to be 10 to the negative 6 minus J. And this becomes minus J 15,915. And then I'm going to approximate this to minus J 16 ohm. Okay. So if you do this, here's where you're going to see where the algebra becomes intense. So now let's go do it. let's go calculate the equivalent impedance here now. So my phasor circuit, so I'm going to convert this into a phasor circuit. So it goes like this here. So I have 36 ohm. I have my cap. My cap is minus J, 16. My inductor is going to be plus J, 10. And so now I want to calculate this equivalent impedance for this circuit here. So then I'm just going to start to use the standard things here. Okay. So if I use the standard things here, I'm going to go like this here. So what I'm going to do here is that I think I'm going to deal with these two first. Since these two are in parallel, I'm going to do that calculation first. So here I go. So then this means here that ZC parallel to ZL, of course, is ZC, ZL, ZC plus ZL, just like we did back in chapter 2. So now that what happens here is that then I got to multiply everything together. So this is going to be what? Minus J 16 times J 10 minus J 16 plus J 10. If you look at up at top here, I'm going to get minus J times J gives me 1. So I get 16 times 10. That's 160 ohms. And then if you look at the denominator, this is minus J. I got 16 minus 10 plus 10 gives me 6. Problem, right? This is a problem. I must get that into the numerator. So what do? I multiply and divide by J. So if I multiply and divide by J, then that's going to give me J 160, and then I'm going to get 6 down here in the denominator. So 6 into this gives me now J 26.70 ohms. And that's what Z parallel to L is. So now I did the first part. So let's go do the next part here. So now what I really have is that I have this here. So what I have here is that now Z equivalent is really the 36 ohm parallel to this guy. Where this guy now is J 26.7 ohms. So now I'm going to repeat the process here. So if I repeat the process, what I really have here is that then this means here that then Z equivalent means it's going to be 36 ohms parallel to J 26.7 ohms. So then here I go. It's going to equal what? Well, the denominator is going to be 36 plus J 26.7. And then I got to multiply both on the top here. So I get 36 times J 26.7. And of course, this will all be in units of ohms. And then guess what? Probably the easiest thing to do here, I don't think I want to multiply by the complex conjugate. I think what I would do now, actually, I'm going to move this over here. I think the best thing to do here is to take this guy and this guy and to convert them into polar form. So if I convert them into polar form, well, the first one is just going to be, so if I look at in polar form, this tells me this here. The first one is just going to be 36 times 26.7. So that gives me 961. And then I get J, but remember J in polar form is 961 e to the j 90 degrees. Okay, I got the first one. We got to get the second one. So the second one, let's do this in polar form. So remember, I got to take the magnitude of this. So this is going to be 36 squared plus, let me move this up here a little bit. So it's going to be 36 squared plus 26.7 squared square root. And then this guy is going to give me 44.8 ohms. Now I got to get the angle. So then theta is going to be the tan inverse, which will then make it 26.7 divided by 36. And this should give me an angle of 36.6 degrees. So this tells me then that now the denominator reads 44.8 e to the j 36.6 degrees. So now I got it in polar form. So now if I go do the algebra, so now I'm going to sub back in. We have Z equivalent, which will then be 961 e to the j 90 degrees divided by 44.8 e j 36.6 degrees. So if I compute this, this will now give me 21.5 ohms e to the j 53.4 degrees, or I can equivalently write this as 53.4 degrees, and that's going to be Z equivalent. Look at that. Right? Look at that. All we tried to do was take these three into parallel. And look at how much work we had to do. You got to admit, that shit is painful. Right? We haven't even gotten a bad circuit yet, right? You can't get easier than that. Do you understand when I say that in 4B, you did not do Phasor circuit? It's like, this is where your calculator becomes your friend. I mean, you want to you want to love your calculator. Wait a minute. I don't want you to love your calculator, but you want to love your calculator because that thing is really, really important in these calculations. And we haven't even done, like, we didn't even apply current divider rule to this thing yet, right? Or we didn't try to calculate the current. It's a painful process. Okay, now that we've seen the first one, let's go to the next one, okay? So the next circuit that we want to do is that now we want to calculate something, okay? And so what you'll find here is that the values that we use become handpicked. That means we come in and we literally walk in and we're careful with how we make the values because we understand that the algebra becomes super, super painful. So let's go do it. We got 5 minutes. I think we could finish this within 5 minutes. So let's go jam this guy out here. So the first thing that we see here is that we got a nice phase, right? So what we're seeing here is that we want to determine the current IT. So that means I have a time domain current, I of t. That means how we're going to do it here is that we then move into the frequency domain. We get I in the phasor form, and the frequency, we get I, and then what we do here is that then we use Euler's to get to get I of t afterwards. So let's go do this. So right away, we could see that omega, is 3 rads per second. So now this tells us we need to convert to a phasor circuit. So here we go. We know that X of R, of course, is just going to be 1 ohm. We see that X of L, which is omega times L, in this case is going to be 3 times 1, which will then be 3 ohms. And we see that XC is then going to be omega over C, which is what? So if this is 3 and 12, so then I'm going to get 12 divided by 3, which then be 4 ohms. Okay? So let's write our phasor vector. So our phasor vector says that I don't write cosine 3t. I then do it like this. I say this is 1 volt, right? 1 volt. My resistance does not change. Now I look at my capacitor. My capacitor is not C, but it's minus J4. That's what the capacitor is. And then, and maybe I should write ohms. And then my inductor looks like this here. And my inductor is then going to read J3 ohms. So if I want this current, right? I'm really calculating this current right here. I want this phasor current. What I'm going to do here is that I'm going to rewrite this thing to read like this. And then this guy right here is going to be what? This is going to be my equivalent. And then I have my phasor current coming in. So then I'm going to use Ohm's law. Ohm's law says that the current I should then be V divided by Z equivalent. Okay, so let's look at this thing. So if I look at this thing, let's go calculate this thing. So the first thing that I'm going to do here is that I got to go get the Z equivalent. So here I go. So Z equivalent, look at that. So I got 1 parallel to those two. So I'm going to get 1 parallel to that. So it's got to be minus J4 parallel to J3. So if I do that, then this is going to be 1. So then I multiply these two together, minus J4 times J3. And then I'm going to get minus J4 plus J3. And you can see that the denominator is just minus J, which is nice. So then this will be 1. Then I'm going to get what? I'm going to get 12 times minus J. So if I multiply and divide everything by J like this, we're going to get a value of 1 plus J12. So we're doing good. But then what I'm going to do here is that I'm going to put this into polar form. Okay? It's easiest to put it into polar form. So if I put this into polar form, then I get 1 plus 1 squared, 2 squared, 12 squared. And this is approximately 12. And then I have theta, which will be the tan inverse of 12 divided by 1. And in this case here, that turns out to be, let's see, the tangent inverse is 85.2 degrees. So that means in phasor form, this is going to be roughly 12 e to the j, 85.2 degrees. So now that I got it in phasor form, here's Ohm's law. Ohm's law then says that the current is going to be V divided by Z equivalent, while this guy is going to be what? This is just guy 1 volt. This guy is going to be 12 e to the j, 85.2 degrees. So if I compute this value, what's 1 over 12? It should be what? 1 over 12, is that 0.83? Because I have some funky number here. I get 0.083 amps with a phase angle of 85.2 degrees. In other words, I can write this as 83 milliamps at 85.2 degrees. So if you're looking at that reactance, you can see that that reactance, this tells me what? So here's what I'm seeing here. What does my phasor vector really tell me here? Well, when I look at my impedance, this is what my impedance tells me. So if I look at my phasor vector, what time do I have? Oh God, I gotta stop. Maybe I should finish this next time. I'll go back in and I'll start drawing the phasor vectors and then trying to interpret what that means. But there's a very specific meaning to that phasor vector right there. Okay, I'll stop right here.